Hello people, welcome one and all to Jojo's Learning Club.
So hello guys, welcome back to my channel Jojo's Learning Club. So today in this video we'll discuss about the energy gap. For to understand about the energy gap, we should first understand what is an energy band diagram. And this is the energy band diagram which shown with conduction band, valence band and energy gap. So energy gap is a gap between the conduction band and the valence band, and it is called the forbidden energy gap or the band gap. So the energy gap at 0 Kelvin, which is denoted as Eg0, and the energy gap 300, which is the energy gap at 300 Kelvin. So for germanium, the energy gap at 0 Kelvin is 0.785 electron volt, and for silicon it is 1.21 electron volt. And in 300 Kelvin, Eg300, you can see the energy band gap, which is 0.72 electron volt. You can see there is a decrease, right? So what happens as the temperature decreases, as the temperature increases, energy gap decreases. And for silicon, you can see it is 1.1 electron volt. As I said, energy gap decreases with increase in temperature. That is, energy gap is inversely proportional to the temperature. So at a certain energy, at a certain temperature Eg of T, it is given as Eg or Gg0, that is the energy gap at 0 Kelvin, minus beta 0 into T, where beta 0 is a material constant and it is already known. And from that, beta 0 is equal to electron volt by 0K. And for silicon, Egt is equal to 1.21 minus 3.6 into 10 raised to minus 4 temperature, that is T in Kelvin. And for germanium, Eg of T is equal to 0.785 minus 2.23 into 10 raised to minus 40. So to understand more about the energy band diagram, let's deal with what are the energy band diagram of metals or conductors, energy band diagram of an insulator, and the energy band graph finally of a semiconductor. So first let's deal with the energy band diagram of metals or conductors. So what is a conductor? Which conducts electricity, right? So all metals are very good conductors of current. That is, they allow a large flow of current through them. All metals are unipolar, which we have already discussed. That is, the current carrying is metals is only by electrons. What's the difference between semiconductors then? Semiconductors are bipolar device, and the current carrying in semiconductors is by electrons and holes. In metals, electron concentration is very high. That is, for example, N, the carrier concentration is around 10 raised to 28 meter cube. Carrier concentration is by electrons, and the electron concentration is around 10 raised to 28 per meter cube. In metals, free electrons is independent of temperature. So this is the energy band diagram at 0 Kelvin and at 300 Kelvin. You can see at valence band and conduction band, there are large number of free electrons in conduction band at 0 Kelvin, even at 0 Kelvin, right? Because they are a good conductor of electricity and they conduct electricity, and there are large number of free electrons. In case of 300 Kelvin, can you see there's an overlap? There's an overlap between the conduction band and the valence band. So overlapping happens as temperature increases. Due to the overlapping of valence band and conduction band, metals have a positive temperature coefficient of resistance. And what is it in the case of semiconductors and insulators? It is negative temperature coefficient of resistance. In metals, there will be only drift current. There is no diffusion current. So what are the examples of a metal? Gold, silver, platinum, copper, aluminium, and etc. And next, about the energy band diagram of an insulator. So as you all know, insulators are a bad conductor of current. That is, they don't allow any flow of current through them. So as you know, energy band gap is inversely proportional to the temperature. That is, the conductivity is 0 in case of an ideal insulator, but practically it is not 0. It is actually in terms of negligible. That is, in a practical case of insulator. Energy gap is large for an insulator, that it will be greater than 5 electron volts. You can see the conduction and valence band, the forbidden energy gap between them is actually a very high when compared to metals. Metals, there is no energy gap, but in case of semiconductors there is a small energy gap. So, and in case of insulators, that energy gap is actually very high. And for insulators, it is negative temperature coefficient of resistance. That is, the resistance decreases with increase in temperature. So what are the examples of a insulator? Diamond, silicon oxide, air, paper, glass, etc. Okay, now let's understand about the energy band diagram of a semiconductor. Semiconductor actually belongs to the fourth group of periodic table. Nature of bonding is covalent bonding, and what other feature it is there? It is bipolar, that is having two different types of charge carriers. What are they? Electrons and holes. For a semiconductor, the energy gap is small, that is energy gap will be there somewhere around 1 electron volt. Why I say 1 electron volt? And for germanium it is around 0.7, and for silicon it is around 1 point something, right? So always for semiconductors the energy gap will be somewhere between the range of 0.7 electron volt to 1.5 electron volt. At 0 Kelvin, so you can see the carrier concentration will be 0, and there is a small energy gap. And at energy gap 300 Kelvin, you can see there are electron hole pairs formed, that is holes in the valence band, and they excite to the valence band and create the electrons in the conduction band. At temperature equal to 0 Kelvin, carrier concentration is 0, thereby conduction band is empty, and hence the conductivity of a semiconductor is 0 at 0 Kelvin. All semiconductors are insulators. They act like an insulator at 0 Kelvin. At room temperature, because of thermal energy, why that thermal energy is created, right? When temperature increases, a large number of covalent bonds will be broken, and equal number of holes and electrons are created, and there will be a small conductivity in the semiconductor. In a semiconductor, there is diffusion current. Semiconductor elements are, some of the semiconductor elements are silicon and germanium. And copper is actually also in the fourth periodic table, but we don't consider it as a as a common semiconductor element. Why? I have already discussed in the previous video. If you wanted to see, just watch the part 3. And there are some reasons behind why carbon is not used. Okay, now let's define semiconductors. So what is a semiconductor? Semiconductors are the elements whose conductivity lies between the conductivity of insulator and conductivity of a conductor. Okay, so we are going next to the Einstein's equation. It is named as Einstein's equation to give respect to the great scientist Einstein. So in a semiconductor, the diffusion coefficient of electrons by mobility of electrons is equal to the diffusion coefficient of holes by mobility of holes, and which is equal to the thermal voltage, where Vt is the thermal voltage. So from here, you know, when the thermal voltage, this term with comes with the temperature, so d by mu, or the diffusion coefficient by the mobility, is directly proportional to temperature, or you can say mobility by diffusion coefficient is inversely proportional to temperature. Unit of d by u is volt. Diffusion coefficient of charge carriers, electron diffusion coefficient dn, which is equal to what? Mu n into Vt. Just cross multiply, you will get dn equal to mu n into Vt. Again, the whole diffusion coefficient dp is equal to mu p into Vt. So unit for d is centimeter square per second or meter square per second. For germanium at 300 Kelvin, dn is equal to 99 centimeter square per second, and dp is equal to 47 centimeter square per second. And for silicon at 300 Kelvin, dn is equal to 34 centimeter square per second, and dp is equal to 30 centimeter square per second. And note, dn by dp, you know that dn is equal to mu n into Vt, and dp is equal to mu p by Vt. Just by dividing it, that both the Vt terms get cancelled out, and where you get dn by dp is equal to mu n by mu p. Just cross multiply, you will get dn into mu p is equal to dp into mu n. Diffusion coefficient can't be negative, and it can't be represented in fraction. That is the most important thing which you have to note while doing problems. Okay, now we are coming back to the most important section of this section, that is the mass action law. It is a very important law which is used in the semiconductors physics. So what is the mass action law? It states that under thermal equilibrium, the product of free electron concentration N and the free hole concentration P is equal to a constant square of intrinsic carrier concentration. So what it is? The product of free electron concentration N and the free hole concentration P is equal to a constant square of intrinsic concentration, that is Np is equal to Ni square. This law is mainly used for extrinsic semiconductor to calculate the minority carrier concentration. So let's say for N-type semiconductors, the majority carriers are electrons, that is Nn, and majority carrier concentrations are minority carrier concentration are holes, that is Pn. Pn you can find from Ni square by Nn. Actually, I made a mistake over here, so I'll just correct it. It's minority carrier. Okay, now let's continue with it. For p-type semiconductors, the majority carriers are holes, that is pp, and the minority carriers are electrons, that is np. So np is equal to ni square by pp. So for an extrinsic semiconductor, as we already said, for an extrinsic semiconductor, what you can find from it, you can find the used to calculate the minority carrier concentration. Okay, so you can, from the minority carrier concentration is equal to the intrinsic carrier concentration square by the majority carrier concentration. So in an intrinsic semiconductor, electrons and hole concentration are np and n and p respectively by adding impurity atoms. So we learn, don't worry about the doping electrons, we'll learn that in the next coming sections. So by adding impurity atoms, the electrons and hole concentration are n1 and p1, then the following relationship is happening. So before doping, np is equal to ni square. After doping, it is n1 into p1 is equal to ni square. Just equating both the relation, you get np is equal to n1 into p1, which is equal to ni square. Intrinsic carrier concentration. Now that's a more important topic. So we were using this intrinsic everywhere, right? So what is actually intrinsic? Intrinsic is actually called the pure. It is a concentration available in the pure semiconductor at a given temperature. So n equal to p equal to ni, that is the intrinsic concentration. And ni square is equal to a0 into t cube into e raised to minus eg by kt, where ni is equal to taking the root of it, root of a0 into t raised to 3 by 2 into e raised to minus eg by 2 kt, where a0 is the material concentration. Intrinsic carrier concentration increases with temperature as a non-linear variation. When compared to silicon, germanium is having large value of Ni, and it is due to smaller value of energy gap. So when an energy gap is smaller, you have a large value of Ni. So let's say at 300 Kelvin for germanium, Ni is 2.5 into 10 raised to 13 atoms per centimeter cube, and for silicon, Ni is equal to 1.5 into 10 raised to 10 atoms per centimeter cube. Okay, so far we discussed about intrinsic concentration, energy band diagram, etc., right? Now the main question, why silicon? Even though germanium has lot of different qualities, why silicon is more preferred over germanium? Smaller leakage current, we discussed that. For leakage current for germanium, it is in the terms of microamperes, and in case of silicon, it is in terms of nanoamperes. So that's a one main difference. And high temperature application, we know the maximum operating temperature for a silicon is around 175 degrees Celsius, and for a germanium it is 75 degrees Celsius. Also, it is suitable for low power and high power handling, plenty of availability on the surface of Earth, and that is a primary reason. So we have a lot available on the surface of Earth, and it is the cheapest material. Favorable properties to form silicon dioxide. So how is silicon dioxide formed? Silicon, when exposed to 1400 degrees Celsius, we get liquid silicon, which react with oxygen to give silicon dioxide. Silicon dioxide is used to provide isolation between the components, and this is one of the main components which is used for the isolation. Silicon dioxide is used to provide isolation between the components inside the IC, and these are the main features why silicon is preferred over germanium. And there is some disadvantage of this silicon too. What is that? The main disadvantage and the major disadvantage of silicon is its smaller conductivity. Okay, with this topic, we are coming to the end of this section, and on the next section, we'll deal with the diffusion current and diffusion. Okay, so that's all about today's video. Thank you and have a nice day.